In this video, we're going to learn about kinematics and going above and beyond what we learned in honors physics related to kinematics. So really specifically, we're adding in some calculus into what we already know about quantities like displacement, velocity, and acceleration. In honors physics, we learned about the difference between average and instantaneous quantities, such as average velocity versus instantaneous velocity. Specifically, we defined those as being average was over a time period, whereas instantaneous was at a set point in time. So we said that the average velocity was the displacement over time, where we understand displacement to be the change in position. Instantaneous velocity at a set point in time is equal to the derivative of the position function with respect to time. We've actually been using instantaneous velocities without really calling them that anytime we did a kinematics problem where we had an initial velocity and a final velocity. If you think about it, those initial and final velocities were at a set point in time, therefore they were instantaneous. We also talked about average acceleration being the change in velocity over the change in time. But now we have the tools to find the acceleration at a set point in time by taking the derivative of the velocity function. Also an important note to something that you might see. We can replace that velocity in the acceleration function with its derivative, dx dt, and we call this a second derivative. We would say this out loud by saying that the acceleration is d squared x over dt squared. Going another step further, since we know that velocity is the derivative of position, we can kind of undo or reverse a derivative using an integral. So the position function is the derivative of the velocity function with respect to time. And similarly, we could do the same with our acceleration function. The velocity is the derivative of the acceleration function with respect to time. So now that we've learned those ideas, let's practice. If you feel confident enough about derivatives and integrals, I suggest you pause this video and attempt these three problems. Even if you're not positive and you're not super confident with derivatives and integrals, go ahead and pause the video and take a stab at least the first question here, using the derivative and integral to find the acceleration as well as the position function for this object that is moving. Notice I left units off here. I didn't want to overly complicate this by putting units in there, but when we actually apply this to a physics problem, we will think about units. So hopefully you paused the video and tried it yourself. I have the answers up here on the screen now. The acceleration is 3.5. The position function is 1.75 t squared minus 12t plus the initial x position. Now remember, when we have an integral that doesn't have limits, so it doesn't have an upper and lower bound, we always need that plus a quantity on there. If you got those answers correct, go ahead and attempt number 2, and you can fast forward this video to see the answer to number 2. But if you need a little bit of an explanation as to where these come from, keep watching. So I'm going to start off with the derivative. We know that this follows the general form that we learned, that if our function is y equals ax to the n power, then dy dx is a times n times x to the n minus 1. So we're going to use that with all of these problems that we have here. So in this case, our a is 3.5, t is our variable, and t is raised to the first power. So in this portion, n is equal to 1. So if I'm taking the derivative, dv dt, which is equal to the acceleration, then I'm following that form, so I have 3.5 times n, which is 1, times my variable t to the 1 minus 1 power. So 1 minus 1 is 0, and t to the 0 power is just 1. And so basically I have 3.5 times 1, which is why my acceleration is simply 3.5. So we have a constant acceleration here, which makes sense because if I were to graph this, I would get a linear graph. And we know that linear velocity versus time graphs give us a constant acceleration. For the integral form, if we have an integral of something that is a times x to the n power dx, again, that dx portion here is just telling us which of those things is a variable, then my function is equal to a times x to the n plus 1 divided by n plus 1, and then it's always plus a constant here. We'll talk a lot more about that plus a constant aspect in upcoming videos. So applying that to my expression for velocity, I have my a, which is 3.5, and actually let's go ahead and write this as an equation. So x is equal to that integral of 3.5 t minus 12 dt. And so I have 3.5 times x to the n plus 1, so n is equal to 1, so that's going to be x squared, divided by n plus 1. So we divide that by 2 here. And then this 12, you could think of that as being 12 times t to the 0 power. And so if I follow that expression, I have 12 times t to the 0 plus 1 power divided by 0 plus 1. And of course I can simplify this into being 1.75 t squared minus 12t. And then I always add a plus a constant at the end. And in this case, since this is a position function, we are going to add a initial position on there. So that's our explanation for the first question. If you haven't yet done so, go ahead and attempt number 2. Pause the video while you're doing it, and then unpause to see the answers and explanation. Here are our answers for number 2. Our expression for velocity was 2.4 minus 7 divided by t squared. Our acceleration, that's our derivative of velocity, is negative 14 divided by t cubed. And our expression for position is 2.4t minus 7 over t plus our initial position x naught. You'll notice this time my acceleration was not constant. This is something we wouldn't be able to analyze last year with our knowledge of kinematics. Let's go ahead and look at how we got those derivative and integral functions. If you got them correct and you feel like you understand it, go ahead and forward the video on to number 3. My acceleration is the derivative of velocity with respect to time. And again, we can treat this 2.4 as a 2.4 times t to the 0 power. And we're following that same rule that what I wrote on that last slide for derivatives. And so I would have 2.4 times n, and n in this case is 0, times t to the n plus 1, sorry, n minus 1 power. And really, if I'm multiplying anything times 0, I just get 0. And then I would find it most useful to rewrite this second term here. That'll be useful for both of ours. So let me go ahead and rewrite it just off on the side here. So I could say that this velocity is 2.4 times t to the 0 minus 7.0 times t to the negative 2. So in this case, this 7.0 is equal to our a, and this negative 2 is equal to our n. So I have 0 minus a times n, negative 2, times t to the n minus 1, negative 2 minus 1. So I have a negative and a negative, and I apologize because this most definitely should be a positive right there. It's an error on my part. So I have 0 plus 14 times t to the negative 3. And another way of writing t to the negative 3 is 14 divided by t cubed. That gives us our derivative. Now let's look at the integral. The x is equal to that integral of, again, writing it out the way that I did before, 2.0 t to the 0 minus 7.0 t to the negative 2 with respect to time. So I have 2.4 t to the 0 plus 1 divided by 0 plus 1, following that same rule that we learned for integrals, minus 7.0 t to the negative 2 plus 1 divided by negative 2 plus 1. Man, I was making some mistakes up here. I missed my positives on both of them. I apologize there. So this simplifies into being 2.4 times t, like you see here. And the other term ends up being plus 7 times t to the negative 1, or that can be written as 7 divided by t. And of course, we need to add on a constant, again, because if we were to take the derivative of this, that constant would become anything. This goes back to what we were talking about last year, where our starting point is unknown if we just know the velocity. So after you've followed this through, if you were not able to successfully find the derivative and integral in number 3, then go ahead and pause this video and try that out for yourself now. If you think you have correct answers, you can keep watching for what the correct answers actually are. So here you see our expression for acceleration and position of our function. We have that velocity function 3t plus 15 over t cubed. Our acceleration is 3 minus 45 over t to the 4th, and our position function is 1.5 t squared minus 7.5 divided by t squared plus x naught. Now this 7.5 divided by t squared, you could also write this as 15 divided by 2t squared if you wanted to not have the decimal and the fraction in the same term. So just like these other videos, I will go ahead and explain how these came up in case you have questions. If you don't have questions, go ahead and skip this explanation, and there is a little bit more at the end of the video. So I'm going to start by rewriting this expression for velocity, much like I did on our last question. 3.0 times t to the 1st plus 15 times t to the negative 3rd power. So if I'm trying to find that acceleration by finding the derivative of that velocity expression, I have 3.0 times 1 times t to the 0 power plus 15 times negative 3 times t to the negative 3 minus 1. Again, those simplify to being 3, because t to the 0 is just 1, minus 45 times t to the negative 4th, which can be expressed as 45 divided by t to the 4th power. My position function is the integral of 3 times t to the 1st plus 15 times t to the negative 3rd with respect to time. And so I have 3 times t to the 1 plus 1 divided by 1 plus 1 plus 15 times t to the negative 3 plus 1 divided by negative 3 plus 1. And then again, plus our initial position. So that simplifies into our expression that we see, 1.5 t squared minus 7.5 times t to the negative 2, or again, you could write it as 7.5 divided by t squared, or 15 divided by 2t squared, and then plus our initial position. This was just an initial demo on this. We will, of course, practice this quite a bit, so hopefully you'll become a bit more comfortable with those derivatives and integrals. I have one last question for you, though. While you now have learned a bit about how to use calculus with kinematics, the question is now, do you always need to use it? And the answer is no. Sometimes we can still use the kinematics that we learned last year, those equations for motion. So I want you to take a look at this question, and I'm not asking you to actually do the question, but I want you to decide, do you need to use derivatives and integrals to solve this? Or can you use the kinematics that we learned last year? Pause the video and take a moment to think about that question and your reasoning for it, and then unpause when you feel like you know your answer. Taking a look at the graph that I see here, I notice that I have a parabola. And a parabola indicates that my position function is related to the time squared. So y is proportional to t squared. And if I were to think about taking the derivative of this function twice, I would find that my acceleration is constant. Even if you're not thinking about derivatives and integrals with this, last year we learned that when we have a constant acceleration, our position versus time graphs are parabolic. When we do have that constant acceleration, no calculus is needed because we have those equations for constant acceleration. So having that determining factor, the first thing you need to do when you see a kinematics problem is ask yourself, is acceleration constant? If it is, you may still use calculus if you really want to, but you could use the kinematics that we learned in honors physics. If it is not constant, then you are required to use calculus to do the problem.